Dear students, uh, in the previous video sessions we have discussed about the working of RTD applications and their constructions. Similarly for thermoelectric principles and their applications and the variations, comparisons, everything we have discussed about the previous video sessions. And this video session we are going to see about the piezoelectric transducers, and we will see this various material used in the piezoelectric transducers, and also how the piezoelectric transducers will convert non-electrical quantity into electrical quantity. So we'll discuss about this in detail about the piezoelectric transducers. Now we are going to see the piezoelectric transducers, but before entering to the piezoelectric transducers, we should understand the basic phenomenon, how the piezoelectric transducer works. Piezoelectric transducers work based on the principle of piezoelectric effect. What is the piezoelectric effect? When two opposite phases of a thin slice of certain crystals are subjected to a mechanical force, then opposite charges are developed on the two faces of the slice. The magnitude of the electric potential between the two phases is proportional to the deformation produced. This phenomenon is called piezoelectric effect. So on considering these definitions, we can easily understand that a substance, when a force is applied to a substance in the opposite phases, suppose this, you have one substance, two phases are there for substance. Whenever a force is applied, either in the top side or in a bottom side, so there is some deformation is produced. It may be not visible by your eyes, but internal deformation only we are talking about here. Suppose whenever certain materials, whenever we whenever we compress the material, or whenever we bend the materials, internally some deformation happens. Sometimes it can be visible in physical also. So here some deformation has been produced. Due to the deformation, we will find electric potential across the two phases of the particular substance. So simply we can see that if you take this as a crystal material, if the force is applied to the crystal material, automatically we will get an output voltage. That means that the force is going to convert it into output voltage. So this crystal material connected to the two electrodes. This is the top electrode, this is the bottom electrode. So whenever a force is applied, automatically the force will be converted into output voltage. And this is the figure which we are seeing here is a quartz crystal, which is in a shape of hexagonal prism. And the various material we can use as a piezoelectric transducers. First one is a quartz, rochelle salt, and last one is a tourmaline. Now, this quartz crystal having some imaginary axes, Z axis, X axis, and Y axis. So three imaginary axes we have. Now we are seeing this Z axis here. Z axis means in a hexagonal prism shaped crystals, if the axis passing through the end point of the pyramids, you can see the end point of the pyramids, an axis is passing, and that axis is called Z axis, or otherwise it is called as an optical axis. And you can see one more two axes are there. One is the X axis, another one is the Y axis. The axis passing through corners, you can see two corners. This is one corner, this is another corner. The axis is passing through corners, it is called X axis, and the other name of X axis is called electrical axis. And if the axis is passing through the midpoint of the opposite sides, this is the midpoint of the opposite sides, then the axis is called as a mechanical axis. So we have this axis are imaginary axes. So based on that we can be able to get the information how it has been placed and how we can slice this, because we are not going to place the same crystal directly to convert into voltage. We will convert this into number of slices, number of piles. So whenever we are converting number of slices, we should know which is the corner points, which is the mid points. That analysis we should have. Then only we can able to place this all the slices to generate the voltages. Now in the previous slides we have seen how the crystals has been made. So these are all three major material we can choose for creating the piezoelectric transducers. But these three metals not having the same properties. If you compare the quartz, it is having the moderate mechanical strength and moderate piezoelectric activity. And if you compare the rochelle salt, mechanical strength is very weak, but piezoelectric activities is very strong. And tourmaline, if you are considered, mechanical strength is very strong, but piezoelectric activity is very weak. Now, among these three, the moderate property belongs to the quartz. So quartz is mostly preferred. Mainly the quartz has been used for the applications of like filters and the RF oscillators, and also we can use this Rochelle salt. Sometimes Rochelle salt also will be preferred. It has been used in the microphones, loudspeakers, phonograph. These are the application of the Rochelle salts. Now we are seeing the construction and crystal pile in a piezoelectric transducers. We can have two figures here. First figure represents the construction, second figure represents the crystal pile structures. When you see the first figures, we have a this is the crystal. It has been placed in an electrode, and this is the area where we are going to give the pressure, the force. And what are the force we are giving? We cannot give directly full force, because we should give a force in such a way the crystal should withstand, because mechanical strength is moderate only for the quartz. Normally the quartz will be preferred. So whenever we are applying the force, that force should be summed and it will be given to this crystal. That means that the force summing member is 1. It will give you a force to withstandable. If you give directly without having any calculation, if you give randomly a force, that can be break this crystal. So this force summing member is used to give the respective force. The force which is the crystal can be withstandable. So that kind of whatever pressure which has been given, based on that, this will be balanced. It will give the stiffness to this crystal to generate the voltage. So this is a crystal placed in a base and connected to the electrode and connected to the force summing member. The force summing member is the one which is used to give the respective force in such a way the crystal should not break. So once the pressure has been given, automatically there is a deformation happens, so it will generate a electric potentials. That electric potential can be measured. V0 will be equal to Q by C. Q is the charge and C is the capacitance. Now this crystal normally it is in nature of, even in the quartz also, even if you prefer quartz also, it is a water soluble whenever we have the temperature variations. So in order to overcome this drawback, we have to pile this crystal. We can make a slice of the crystals, and you can see that crystal has been made as a slice, and this crystal has been placed in a housing that is called transducer housing. There is a base actually. Now one end it has been placed in a transducer housing, another end it has been placed in a load plate. Load plate is nothing but the plate where we are going to give a pressure or force. Now to balancing, for example this force summing member, we are using as two springs to balance, because whenever a pressure or force has been given, this should not break these crystals if the force is more. So this will be having the stiffness, and this also having the stiffness. So whenever there is a pressure has been given, so deformation occurs, and this also will be more flexible. The spring will be get flexible, and some deformation happens here. So due to that, we will get an output voltage will be taken from the, even sometimes it will be taken from the individual piles, and sometimes it will be taken from the whole crystals. So now we are going to see how it works. Already we have discussed how it works. So the crystal is placed between a solid base and a force summing members. So we have a 2 ends. The crystal has been one end we have to place in a base, another end we will be placed where the force we are going to apply. So metal electrodes plated on the faces of the piezoelectric crystal are taken out to measure output, because we cannot take directly from the crystals. We have to connect both the end 2 electrodes. From there only we can able to take the output voltage. The electrodes become plates of the parallel plate capacitors, thus it can be considered as a charge generator. So normally capacitor means 2 parallel plates separated by dielectric medium. So here also we have 2 plates. That means you can see that in the previous slides we have 2 electrodes. 2 electrodes only taken as a 2 plates of capacitors. So in between we have a crystals. So that is we are saying as a dielectric medium here. So the electrodes become plates of the parallel plate capacitors, thus it can be considered as a charge generators. Since the crystal are water soluble and dissolved in a humid environment, the output voltage is affected by temperature variations. So to overcome this, we have to place the crystal either it should be connected in a springs, or it can be connected in a diaphragm, or it can be connected in a tube loaded. So these are the ways we can able to overcome this drawback of the water soluble. because in the environment we have a lot of humidity, a lot of moistures, so that cannot make the crystal should be soluble. So in order to overcome that, we cannot directly open environment, we cannot able to give the pressure to the crystals to generate a voltage. And this transducer specialty is we cannot require any external voltages. So since this transducers come under the active transducers. So the crystals are made in the form of pile of pairs of quartz discs. These discs are placed between the transducer housing and the load plate. To support the crystals while applying pressure, preloading springs are connected along with the crystals between the transducer housing and the load plate on both the sides. So this preloading springs, we can already we have seen that what is the purpose of preloading springs, which will give the support to these crystals to avoid the crystal breakdown. And this K2 by 2, because we are going to use two springs, so both the spring having some stiffness, and that should able to support these crystals, and it will use to do the operation in a linear manner. Now stiffness of the crystal also we can denote as K1. In the previous slide we have seen that how the piezoelectric pressure transducers works along the spring. Now the spring has been replaced by the diaphragm and as well as the tube loader. So both the purpose, diaphragm and the spring, is used to give the stiffness, and it is used to give the operate the linear operations, because the crystal should not break whenever the pressure has been applied. So here also the crystals has been sliced in such a way, the one end has been placed in a housing, another end is connected to the diaphragm where the pressure is going to apply. So whenever the pressure is applied, automatically the deformation happens, we will get the output voltage. Here also the crystal has been sliced and placed in a housing, and another end has been placed in a thin diaphragm, and also surrounded by the thin wall tube. Now whenever the pressure has been applied, automatically we will get the deformation, we will get the output voltage. The pressure which we are applying, we can classify into two types. P equal to P1 plus P2. P is a force produced by the external pressure, and P1 is a force in the crystal pile. P2 is a force in the preloading thin wall tube or diaphragms. So P1 plus P2. The del X, what is meant by del X? The deformation which happens inside the crystals, and also the change in the stiffness of the diaphragm or change in the stiffness of the wall tube. That is nothing but the del X. And K1 is the stiffness of the crystal, and K2 is the stiffness of the diaphragm or tube loader. Now P1 related to the crystal, so we can say that K1 into del X. K1 is the stiffness and del X is the change in that deformations. K2 is the stiffness of the diaphragm and del X is the compression. Now we can take the del X as commonly outside, so we will get K1 plus K2. If you take that ratio between the P1 divided by P, P1 divided by P, P1 we know K1 into del X, and P is equal to K1 plus K2 into del X. So del X will get cancelled, so we will get K1 divided by K1 plus K2. So we can divide the numerator and denominator both by K1, so we will get 1 by 1 plus K2 by K1. So according to this relation, why we are doing this? According to this relation, if K2 by K1, this value, if it decreases, automatically the P1 by P value is going to be increases. According to this piezoelectric transducer phenomenon, this K2 by K1 ratio should be maintained as constant. That means that suppose whenever the pressure is applied, if this diaphragm or a spring will giving the more flexible, and if the crystal is getting the more pressure, then the crystal will break. Our crystal is not getting the more pressure, and even if the diaphragm is getting the more pressure, then we won't get the output voltage. So the variations, that means you can see the compression has been done equally, both the diaphragm as well as both the crystals. So if this ratio has been maintained constant, then we will get that output voltage, the required output voltage. Now we can see the advantages and disadvantages of this piezoelectric transducers. It is rigid in constructions and smaller in size. It is having excellent frequency response, linearity. External power supply is not required because it belongs to the active transducers. Apart from that, we have so many disadvantages. It is more temperature sensitive because we already seen that it is a water solubles, and it is used for only dynamic measurement. So this cannot be worked for static measurement categories.